So next method is method 25, where we were looking at the gaseous non-methane organic emissions. This method, we use it when we want to determine the VOC measured as total gaseous non-methane organics, which is TGNMO, and reported as carbon. So what does that mean? It means that sometimes you really don't care if your compound is benzene or toluene or hexane or whatever it is, or chloroform. What you want to know is the VOC total, so that you can compare it with the limit to show compliance. And in this case, you just need a number. So, but why is non-methane? Because methane is not part of this group. Methane is not part of the VOC. So that's why this method measures everything except methane, and you report it as carbon. So, for example, CH4, that's methane, has 1 carbon. So its molecular weight is 12 plus 4, that's 16. So if I have, from this method, 10 milligrams per liter, I will multiply the 10 by 12 over 16. This will get you the carbon amount that's in this concentration. Let's take another, if it's methanol, CH3OH. So I will get the total molecular weight, C12. Now we have 4 H's, so that's 4. So now we have 16, and we have 1 O, which is another 16. So the total is 32. So the carbon amount out of it, carbon fraction, will be 12 over 32. So, and we do this with every compound to know what is the carbon amount that is there. The cost, logistics, and other practicalities of source testing may make other test methods more desirable for measuring VOC contents of certain effluent streams. So this is an expensive, and proper judgment is required in determining the most applicable VOC test method. So in this method, sample is extracted from a single point at a rate proportional to the gas velocity. So we will have, again, if this will be my stack, and I will have an opening, I'll put my probe inside the stack, and I will get out Q, V, and I will want to make sure that I determine what is the Q and the V that I get out of it. This is Q and V is very different than the Q and V inside the stack. So this is Q stack, V stack. This is Q sample, V sample. Sample is separated into condensable and non-condensable fractions. What does condensable mean? Condensable means that it can condense as a liquid. So have you ever seen glasses when you go to Dubai or Abu Dhabi in the summer having all this water on top of them? So you don't wear glasses. Sometimes. So it's very common that you will get water that just gets on top. So why this is happening? This is happening because some water is condensing on surfaces. That comes from the humidity of the air itself. Imagine this flow that's going through the stack. If it has humidity, and depending on the temperature, sometimes it's very likely that the water inside this will condense. So let's say I am collecting in this balloon the gas. So I will have here some liquid, and then I will have here some gas. Okay, so that's why in this method, we take the sample, and then first we take the condensable part out, and then we leave the non-condensable part. So we have two things to sample in this method. Analysis yields total gaseous non-methane organic emissions as carbon. So looking at this over here on the graph, This one is the stack, the one that I'm putting in red right now. Now you can see the probe. The probe goes inside the stack right here. And the sample goes here. This is a thermocouple. Thermocouple is used for measuring the temperature because temperature is very important to know, right? And usually the probe is stainless steel probe. This box is heated. This one is a heated box, the one that I'm drawing right now. Why is it heated? It's heated to maintain the temperature. Exactly. So there is a temperature controller that to set the temperature to the required value. And then you get filter holder. That's this one over here that has the filter inside. You have a sample valve, and then you have two pathways. This is a vacuum pump. This one is a vacuum pump that is connected to a rotometer. A rotometer is a measurement of the flow. Rotometer measures Q. So, or adjusts Q. So based on the vacuum pump, we actually make sure that the sample goes this way. This is how we determine what is the V or the Q that's coming out based on the actual V or Q here. And then the force that we are putting here, it pulls the sample. So now I know what is the V or Q here. That's coming this way. So the first, it goes through what we call condensate trap. This is a condensate trap. What is a condensate trap? Is a U that's put in an ice bath. Why? To cool down the stream. When it cools down, what happens? Water will settle. So here, the condensate will be in this U, and then the rest will go here. This one, the sample, will go into this tank. This is the sample tank. And this is manometer just to measure the pressure. So it's a very complicated setup, as you can see. And this is how we collect the sample. So an emission sample is withdrawn from the stack at a constant rate through a heated filter. Now, if I ask you why a heated filter again? So why do we heat? Think about what's happening later. What is happening later? We are condensing the water. So if we don't heat, actually it will cool down and it will condense right there, not where you want it to condense. So you need to keep it heated until you start condensing. The heated box is going to the condenser. Yeah, otherwise the water will condense in the pipe and then it will be blocked. So you will not have flow. Okay. So a chilled condensate trap by means of an evacuate sample tank. So TGNMO is determined by analyzing the condensate trap. So you will take the water out of here, take water, and you do analysis on the water. So we will oxidize the NMO to CO2, that's number one. Quantitatively collect the effluent in an evacuated vessel. Then a portion of the CO2 is reduced to CH4 and measured by an FID. An FID we talked about in the last video, and it's called flame ionization detector. Now this is for the liquid. For the gas, we will take and inject portion of the sample into a GC column. We'll separate the NMO from the CO, CO2, and CH4. The NMO are oxidized to CO2 and then reduced to CH4 and then measured by the FID. So we need to take the carbon that doesn't belong here, which is carbon monoxide, carbon dioxide, and methane. You take this out and measure the rest. Then we'll have sample number 1 from the liquid, sample number 2 from the gas. You combine 1 plus 2, you get the total. And that's the combined TG-NMO according to this method. Any questions? Non-methane organics. So this is how it looks like in big. So let me just clear. So you can see the stack wall, you can see the sample holder, the condensate trap, the sample tank where the sample is collected, the vacuum pump to make sure that you get the required flow rate and velocity, and so on and so forth, and another rotameter to make sure that the Q is what you are looking. This is the setup for method 25. Now there is method 25A, which is used to measure the gaseous organic concentration using flame ionization. So this is a variation of method 25, and it measures the total organic concentration on a continuous real-time basis. Remember the 25, you collect the water and you collect the condensate and you collect the gas and you take it for analysis. But in 25A, you actually do it continuously. So you have an FID on site and you can keep measuring it in real time. Method is best applied to measure vapors of consisting primarily of alkanes, alkenes, or aromatic hydrocarbons. Gives reduced response to compounds that are highly substituted or chlorinated. So you don't want to use it if you know that you have chlorinated gas. Here is the sampling train of method 25A. You can see the stack wall, similar to, and the heated probe, particulate filter, similar to earlier. You get here a 3-way valve. So usually it goes into this, or sometimes we use calibration. Why we use calibration? Because we need to make sure that my detector always gives me the right concentrations. So every now and then I have to stop the real-time measurements and measure a standard, measure a sample that I know it's 10 parts per million. And then see, do I get 10? If I get 10, all good, I switch back to my sample. But if I get 5, means something is wrong and I need to adjust. So that's why we have a calibration gas right there. So then it goes into a vacuum pump that pulls your sample and puts it. Could be a dilution system if needed, if the samples are high. So we get air from out and we mix it, the air that comes in the vent, and mix with the sample and goes here. So this will be Q1, this will be Q2, and this will be Q total, which is Q1 plus Q2, and goes into dilution system and then finally to the FID analyzer. So at the end of this chapter, I just put this 2 slides to use for you, they are very useful in a lot of things, not only for this chapter, but also for a lot of other calculations that you need to do. So make sure that you have them in the final exam. In this, we have values that are in different units. You have a lot of, you have Antoine's equation, and you have a lot of substances with their formulas, with the range of temperature, and the ABC for Antoine's equation. Antoine's equation was covered in the last video. Also, table of acronyms that I thought would be helpful just in the exam. If there is something that you forget or you don't know, you have to go through all the slides. Make sure that this slide is handy so you know what is ACFM. I know I asked you last lab and lots of you didn't really know what it was. So that's why I put this here, just to make sure that you guys have access to this inshallah, maybe even in the future, you can look at this slide, have it in your office. So whenever you have an air pollution problem, you can usually go back to it and look at it. And that's it for today's class. Thank you for listening.